Assalamualaikum everyone. This is lecture 9 on Control System Engineering 1. We are covering chapter 4, the time response or the transient behavior. So in the last class, we have started with some basic idea and definitions. And then we have seen the first order system and the parameter corresponding to the first order system. Basically, one system parameter was there, A, and based on that, rest of the parameter is being calculated. So the things are not as simple as your first order system. In the last class, we asked one question that is it possible to have an oscillation in a first order system? So the answer is no, it is not possible because of the fact that in the first order system, the response is always based on your system pole location. So basically e to the power minus AT is your system's behavior. So it always gives an exponential response, and if your complete response is 1 minus e to the power something, then it will always have a nature or something like this. Okay, so based on the value of the A, if A is closer to the imaginary axis, then it will take more time to reach. If A is far away, then it will take a very small time to reach the steady state value. Okay, so this is how it is related in the first order system. So, in today's class, we are actually going to see the second order system, and the second order system is not as simple as your first order system, and as well as a few other form of response is also available. So in the first article, that is article 4.4, second order system and introduction, actually we're going to see the numerical values and how they are related to our system response. So these are the things that we are going to see initially. Then in the next article, basically article 4.5, we'll formally try to find out the corresponding equations related to the second order system. So let us now begin with the second order system. So what is the second order systems different from the first order system? First of all, it exhibits a wide range of responses, not only one damped or exponential nature, rather it will have free oscillation. Okay, so all these kind of possibilities are there. So basically 4 of them. So we'll be discussing them in detail in this section. And also we have to relate our parameters of the second order system, how they're actually causing these changes in the form of the response. So don't worry, without further ado, let's go into the analysis first, numerically how they are related. And then we'll try to see how they will be relating in what is their corresponding equations and formulas. So this is actually figure 4.7 for your simplicity, so that you can refer to there. So we are actually trying to discuss the figure 4.7. Okay, so the first portion of the figure is giving you a generalized second order system. So in the second order system, there may be 2 pole to 0, but as we already know, the contribution of the 0 is actually only in case of the magnitude, what should be the magnitude of the responses. So that is why we, in generalized form, we just discuss about the poles, not about the 0. So let's say we have a block diagram, generalized block diagram representation of a second order system, something like this. So this is the step input. Maybe in general we use step input for checking the system behavior and the responses. So then you have the generalized form of g of s for the second order is given by b by s square plus as plus b. Okay, and then you have your c of s. So if you try to find out the root of this equation, so the root of the denominator or the poles, so if you want to figure out, then you just apply the quadratic equations so basically minus b coming from s actually s square plus as plus b equal to 0. If you put that, then minus b, okay, plus minus b squared, that is a square minus 4a into c, that is 4b divided by 2. So as you can see, we have minus a by 2. This is real part. Then based on the value of a and b, there is a possibility for you to have a real number or imaginary number in the second portion. So we are keeping real for now, but it can also be imaginary. So base actually this is the thing that is determining what should be the system response. Okay, so let us go for some numerical example, as we already said that. So now in figure B, we have a transfer function something like this. So 9 by s square plus 9s plus 9. Okay, so step input as well as 1 by s. So now let's see what is the pole location. So if you apply S12, then you are going to say get is minus b, that is 9 by, okay, so minus 9 plus minus root over 9 square minus 4 into 9 divided by 2. So if you do that, you're going to get two values, minus 1.146 and minus 7.854. So if we now plot those in the S-plane, so one of them will be somewhere here, minus 1.46, and the other one will be somewhere here, minus 7.854. So basically both of them are real, and both of them will give a response, exponential response. So basically what output we are expecting because of the force input of 1 by s, because of it we are actually going to get the final value of 1. So your final value you're going to get is 1, so no question about it because of the input. So, and because of these two damping nature, so this one will be decaying fast, this one will be decaying gradually. So a combined decaying will be observed, and you are going to get something like this maybe. Okay, so eventually it will merge with that one line. So what should be the pattern of your CT output? We know there is two roots, so definitely one. Okay, so 1 plus, we are just keeping plus, but it depending on the value of K1 and K2, it may be something else. E to the power minus 7.854t plus K2 e to the power minus 1.4146 t. So this is how the response will look like once you know the pole location. So this is how you can relate with the pole location of the response. So what this particular case is known as over damping. Okay, so over damped response. Over damped response. So why we are calling it over damped? Because of the fact that two of the root is actually causing the damping. So excessive damping is there. So that is why this is what is called over-damped response. So this is the first case. Actually, in the figure 4.7b, all the values of K1 and K2 is given. So you can actually have a look at that one. But we're actually trying to relate our response with the system that is being given and where the pole locations are. Okay, so the next scenario is we have a pole, we have a transfer function, something like this. So 9 by s square plus twice s plus 9. Again, step response, step input. So step response is what we are going to get. Now, what will be the location of your S1 and 2? So S1 and 2 will be minus B. So minus 2 plus minus root over B square, that is 4, minus 4AC4 into 9 by 2. So 4 can be taken common. So what we can have is minus 2 plus minus 2. Then you have 1 minus 9 by 2. So basically 1 minus 9 is minus 8. So minus root over minus will produce the j, and the 2 can be cancelled from the equation. So minus 1 plus minus j root over 8. Okay, so what we can see here is in this particular case, the root is, the pole is having uh, the real component as well as imaginary component. So real component will give an exponential part, and this one will give you a cos and sine. So you can actually write in terms of cos omega t, sine omega t, then summarize to find out one particular value. So we will have something like root over 8 t minus 5. Okay. So this will be your nature. And don't forget, this is only because of the system poles, not for the step response. So for the step response, 1 minus something like this. Okay. So what does it mean? First of all, let us try to look at the pole locations. So pole locations, this is maybe 1. So and say this is root over 8 somewhere here. Similarly, somewhere here. So this is your pole location. Minus 1, then you have j root over 8 minus minus j root over 8. Okay, so if you have a complex conjugate, so basically always you will have 2, and there will be mirror image to the real axis. So it always comes as a 2 because of this, the solution of this quadratic equation. Okay, so now what should be the type of the response? Now, because of the my real portion, it will have exponential decay, and because of this imaginary, you will have a sinusoidal oscillation. So what we are going to get as a response, forced response, again, it will determine the final value. So say final value is 1 in this particular case. So what we are expecting an oscillation, and the decaying oscillation that will approach eventually to 1. So we will have something like this, a decaying oscillation maybe. So this is the scenario. Is it okay? So the response we already calculated, and so this is what will be your CT. CT will have a pattern like 1 minus some coefficient K. So you have to figure out from the partial fraction expansion. So the book says it should be 1.06. So whatever it is, so you just put that value, then you have cos root over 8t minus 19.47. Okay, so we're not that interested about these magnitudes, but we're just trying to relate how the pole location is related to the system's response. Okay, so this is second case, and what do we call this one? We call is we are reaching to the final value undergoing through an oscillation. So and also there is a damping case. So this particular case is known as underdamped response. So underdamped response. Okay, going through the damping, you are reaching to the steady state value eventually. Okay, so I'll be asking one question once all the cases been discussed, that which one is actually suitable or desirable for our system. So this is a question you always have to keep in mind. So whenever you are learning something, so which one you prefer, which response may or may not you can achieve, but depending on the system, existing system, then you have to go for the controller. That is the thing. But you should always have the idea, like the elevator. So elevator reaching a particular level, say level 5, whether you want the oscillation to be there while it was stopping, or what kind of response you want. So this is what you have to keep your mind open so that you can uh, realize what is actually happening. So now we have discussed two. One is over damped, too much damping. One is under damped, so oscillation. Then the oscillation is disappeared because of your damping. So this is under damped. Now case 3 is actually what we have with the transfer from block diagram representation, something like this. 9 by S square plus 9. So again, same thing. If you want, I think I should stop repeating these. Okay, so now S12, which will be coming from definitely from this one, will be uh, plus it will be S square is equal to -9. So 1 over -9 is basically plus minus J3. So if you plot in the S plane, you have one maybe here, another maybe here. So this is plus J3 and this is minus J3. So now as you can see, there is a sigma. Sigma value is 0. Sigma value 0 means e to the power minus sigma t was the case, isn't it? The exponent decaying function. So this is not present. What is left is only cos omega t, maybe 3t minus 5. So this is what is left. And also don't forget about this step response. So your final response will be something like this. Ct will be equal to 1 minus or plus, depending on the value of the k. So we generally keep it k cos 3t minus 5. Is it okay? So now, what should be the system's response? Uh, System response, again, it should go to 1, but it will not go because we don't have any damping, but we have a pure oscillation. So basically, the value 1 is always now the reference with respect to which it will oscillate, but it will oscillate maybe equal magnitude, something like this. But it is never actually getting reduced, is always having same pattern. Okay, so sinusoidal, even though drawing the tab is not that perfect, but just assume that this is a sinusoidal oscillation. So around the value 1, it is always oscillating. So it is never decaying because of the fact that the exponential component, decaying component with the power sigma t. Now here the sigma is actually 0. So that is why it is always sustaining oscillation. So what name it should be given is basically undamped, without any damping. So that is why undamped response. Okay, so one thing we actually forget to discuss in the last one is what is the frequency of this oscillation. So this frequency of oscillation is called natural frequency omega n. because without the damping, whatever the frequency, that is your natural frequency. And also the frequency that we are having here, which is not definitely natural frequency, but it is a combination of natural frequency with damping. So the frequency of this one is known as damped frequency of oscillation. So we call it damped frequency of oscillation. Okay, so we have to keep it in mind and we represent it in terms of omega d, damped frequency of oscillation. So third case is also discussed. The first was over damping, too much damping was there. Then the other one is under damping, so it's damping and oscillation. Then the third one without any damping, so basically undamped response. Now we have a pure sinusoidal movement around the reference, that is actually your step input. Now the fourth and the final case is what will happen if you have something like this. So 9 by s square plus 6s plus 9. So now you have repeated roots. Both of them are real and they're repeated. So basically s plus 3 whole square equal to 0. So s will be basically both of them is minus 3, minus 3, minus 3, s1. So in terms of the S-plane, you have both in the same locations over here, so minus 3. So what will be system response type? So before going to system response type, what should be the equation? If you know from your partial fraction expansion, you'll have something like this, K1 by S, then you have plus K2 by S plus 3 whole square plus K3 by S plus 3. Okay, so because of this square term, we're not going to figure out what is K1, K2, K3. I think you will be able to do that from the knowledge of the chapter 2. But from this one, if you can take the inverse Laplace transformation, we say that in K is 1, so we can K1 can be 1 if you calculate. So 1 minus or plus K2 e to the so because of the square you will have t e to the power minus 3t plus K3 e to the power minus 3t. So you have an additional term. So both of them in the same location will actually produce the fastest response without any oscillation. So any value after that, it will actually go for oscillation. So it will be the fastest response possible. Okay. And this is what is called critically damped. Critically damped. Okay, why it is critically damped? But next instant will be actually, this is a borderline uh, in between the underdamped and in between the underdamped and your damped oscillation. So damped scenario. So because of that, we call it critically damped. So basically what happens, I'm not sure whether you have noticed or not. So what was happening is, what happens in general is, for a system, if you start changing the pole location, so they will be at a over damped condition. Then gradually they will be merging to a same location. So this is what is called critical damped. Then they will be merging going towards your real imaginary axis. Okay, so this is how it evolves. So that is why whenever they are actually equal, then we call it critically damped. So this is the boundary between the real and having a real and complex pole. Okay, don't worry, we'll discuss all this later on, just for understanding why we have given a name, something like this. Okay, so this is how what are the 4 scenarios you have. First of all, definitely overdamped, then you have underdamped, then you have undamped, so pure oscillation, and then you have finally the critically damped, so first test response without any oscillation possible. Okay, so these are the scenarios, all four scenarios. Okay, so they have given one example of underdamped case. So let's also have a look at that one. Example 4.2. Example 4.2. Okay, so a system given with step input is 200 divided by s square plus 10s plus 200. Okay. So what type of response you're expecting from this system? So this is what you have to figure out. So is it difficult? I don't think it is difficult. So what you have to do is just you check what is their pole location. So S12 is minus 10 plus minus 10 squared, that is 100 minus 4 into 200 divided by 2. So basically minus 5 plus minus root over 300, sorry, 200, 800 minus, so 700, 700 by 2. So what you can say, oh, sorry, one thing I forgot is there is a minus. So because of the minus sign, we will have minus 5 plus minus j something. Okay. Now tell me what should be the system response. So system response, sorry, first no. So system having some real component, the pole has some real component, the pole has some imaginary component. So it will go into a damped oscillation. So something like this, the system response. So by just from the system's pole location, you can say what should be the type of the response you're expecting from a particular system. Okay, so things are not that complicated. Now, if we summarize whatever we have seen in this article is the case one is overdamped, over damped. So what we see is sigma 1 was maybe one location, sigma 2 can be another location. So based on that, your time response can be K1. Only the system, we are not talking about the step response. So A to the power minus sigma 1t plus K2 e to the power minus sigma 2t. Sometimes my sigma is similar to 6, so you just have to be a bit careful about it. Okay, so this is the first case. The second case was under damped response. So under damped. In that case, what we had was we had real portion as well as we had imaginary portion. Okay, so something like this. So damped, that is why sigma d, and damped, that is why omega d. So damped frequency of oscillation and also damping effect, the frequency, exponential frequency you can call it. Okay, so what type of response we are expecting from this one, from the systems, is actually it will have some magnitude, just like here, constant, as well as it will have some damping effect, sigma dt. As well as the frequency of oscillation with cos omega dt minus 5. Okay, so now go to the third case. Third case that we were discussing was uh, undamped scenario. So undamped scenario. So in the undamped case, both of them are actually imaginary. So we can say that plus minus j omega, omega 1, omega d, whatever. So if you have something like this, so what kind of response we are expecting from the system only? A cos omega t minus 5. Okay, so there is no delaying effect, sorry, decaying effect, only you have your pure oscillation. Now the fourth case was critically damped. Critically damped. What we had was there, we had same location, both of them was same location, maybe sigma 1 or sigma, so same location. So what was the scenario here? Because of the repeated rule, you have k1 t e to the power minus sigma t, then k2 I to the power minus sigma t. For simplicity, you can give 1, 2, or any specific value if you want, similarly here, but it's up to you. Okay, so 4 different scenario and 4 different type of responses possible. And you have skill assessment exercise 4.3. I will expect that you will be covering it by yourself because just the equation, and based on that equation, you have to inspect the pole location, and based on that, what type of response you are going to find. But we are not expecting you to find out numerically, just analytically. So you can use the coefficients A, B, K1, K2, something like this. So that's not a big deal. Okay, let's go to the next topic, next article. So next article is actually 4.5. So it is the general second order system. So now we are going to go to define the characteristic equation in terms of not general parameter like AB, rather the system parameter that we had, the second order system. So in terms of that. Okay, so the general article title is the general second order system, the general okay. So before going to defining that, two quantities actually we want to find out the quantitative specification of the second order system. For that we need two quantities. Two quantities is required. So one is called natural frequency, and the other one is called damping ratio. Okay, one thing you have to be careful is basically this damping has no relation with your viscous damper. So this is a more of a related to the curve or the pattern of the signal, but there is no relation with this one, with your frictions damper or something like this. Okay, so these are more of mathematical thing, okay, no physical thing. So let us so what do you have to do? You have to use this to describe the characteristic of the second order transient response. So this will help us to characterize. You can use S or Z, whatever you like. Characterize the second order transient response. Okay, so now let us define these two first, and then we'll go into the formal general second order system representation. So what is omega n? So natural frequency omega n. So what is omega n? If the oscillation of the system without damping, that is what is called natural frequency of oscillation. So oscillation without the damping. Frequency of oscillation. So if you want, I can write, or uh, frequency of oscillation. Oscillation without damping. Okay, so maybe you can consider the RLC circuit. The RLC circuit, if somehow the resistance is shorted, then energy will be just transforming from inductor to capacitor, capacitor to inductor. So it will create a pure oscillation. Okay, so this is your the resistor actually acts something like a component that actually the energy is being absorbed. So if there is any absorption, then energy will be always transforming from the capacitor to the inductor, inductor to the capacitor. For that also, capacitor and the inductor, we should also have no impedance or no resistance at all. Okay, so this is your natural frequency, the straightforward. The second one is not as straightforward as this. So the second one is called damping ratio. Zeta. It's difficult to draw as well. So zeta, damping ratio. So actually it is defined by comparing the exponential decay frequency of the envelope to the natural frequency. Yes, I know it seems complicated. So what we are trying to do here is we are trying to actually relate, if you draw the diagram. So if this is your reference around which you do final value, so we will have something like this. Okay, so maybe gradually it will be merging with that one. So now you have exponential decay. Okay, so exponential decay, this is one thing. And also you have a natural frequency of this one if there was no damping. So omega n is your natural frequency and the exponential decay is also there. So your zeta is actually a relation between them. Okay, so mathematically, if you try to write it, so your zeta is exponential decay frequency divided by exponential decay frequency divided by your natural frequency. Okay, so this is how it is defined. Now, one thing you have to be careful is this ratio is not time dependent. So this is a general pattern. Actually, if you have oscillation, how this oscillation is decaying with respect to the natural frequency it possesses. So this time scale can be seconds. It can be microseconds, or it can be millennia. Okay, so it's not dependent on the time. So whatever the time scale, it doesn't have any difference on it. It is always following a pattern. So the time may be too short as microsecond or nanosecond, or it may be too long as millennia, but still it will possess a same ratio. Okay, so the ratio is basically how exponentially it is decaying with that with the natural frequency. And so sometimes you can also express the natural frequency decaying, as we know from the previous first order system, an exponential decay frequency can also be inversely proportional to time constant. So we can also say exponential time constant, inversely proportional exponential time constant. And the natural frequency, you can also represent it by in terms of time. So natural period. So 1 by twice pi, 1 by twice pi natural frequency, and if you invert the frequency, then you are going to get the natural period. In seconds. Okay, so this is how you have to define your damping ratio, a ratio that always been maintained in between the exponential decay frequency of the envelope and the natural frequency. Exponential decay frequency of the envelope. So envelope of this pattern that we are following. Okay, and your natural frequency of oscillation. Okay. So now, from these ideas or the definitions, let us try to find out the generalized second order system. So the system that we already discussed in the last segment was something like this: G of S equal to B by A square plus AS plus B. Okay, so now we want to represent this system in terms of zeta and omega. Okay, so without damping, the pole location will be always in the j omega axis. So if there is no damping, so there should be a pure oscillation. So pure oscillation is only possible if your poles are having here. So from this equation, from the denominator especially, so what condition we should have? We should have a equal to 0. So if a equal to 0, sorry, I should have s square. So if a is equal to 0, then you have s square equal to minus b. Then you have it should be equal to plus minus j root over b. Okay, so this is your pure oscillation, isn't it? So pure oscillation, so we can relate this one with your natural frequency. So without any damping, so A is something that is related with damping. So if A is not there, we have pure oscillation. And according to the definition of the natural frequency, without any damping, whatever the frequency that you are getting is actually your natural frequency. So this is what we get. So we can say that B can be omega n squared. Okay, so this is first thing. So we can replace this into that equation. So what we are going to get here is g of s equal to omega n squared. Then you have s squared plus as plus omega n squared. Now what is left is a. We have to change the value of a. Now we also have seen that the equation that we had previously, s squared plus as plus b. So if from this one we try to figure out what was s12, and we have seen that a, it was a by 2, then you have plus minus root over a square minus 4b by 2. So it was the case, isn't it? And this is related to frequency, so we are not bothering about it. But what we can say, this is your exponential decaying frequency, isn't it? So what we can say that this is actually nothing but your sigma value. So we represent e to the power minus sigma t, or e to the power minus a by 2t. So what is the definition of the zeta? The definition of the zeta is exponential decaying frequency divided by natural frequency. So exponential decaying frequency is sigma. We are giving it magnitude, taking the magnitude because it will be negative in magnitude. So we are just getting the numerical value. And then you have the natural frequency omega. So we already have seen that your sigma is nothing but a by 2 magnitude wise. So this is what we have. So we can say that A can be represented by 2 sigmas omega n. So now from that equation, we can find out our generalized second order representation is g of s equal to omega n squared s square plus twice zeta omega n s plus omega n square. Okay, so this is your generalized second order system. Now, question is, what is the pole? What is the pole location of this system? So, pole location of this system, if you want to figure out, then we have to solve the denominator. So, this is our second order systems general representation. So, now we are interested about finding out what is the location of the pole. So to find out the location of the pole, we have to set s square plus twice zeta omega n s plus omega n square equal to 0. That will give us s12 equal to minus b, that is minus twice zeta omega n plus minus b square, that is 2 zeta omega n square minus 4 a c divided by twice a. Okay, so you can easily see it. You can be deducted from the whole equation because it will be 4 here as well. So if you take 4 common, 4 will be going outside. So as a 2, so 2 can be cancelled out. So minus zeta omega n plus minus root over zeta square omega n square minus omega n square. Okay, so what is left is minus zeta omega n. Then you can also take common the omega n square. Okay, so we have zeta square minus 1. Okay, so finally, you can write something like this: minus zeta omega n plus minus omega n root over 1 minus, sorry, zeta square minus 1. So zeta square minus 1. Now, what should be the system's response? So we'll be going later into that, but what you can see here is in the Plask article, we have seen the relation between the pole location as well as your system's response. Now we can say that pole location is actually a contribution which is specifically because of the value of the zeta, because depending on the value of the zeta, we can have all the 4 conditions required for the second order systems for different type of response. So let us try to relate those and see how they behaves. And now, say, first of all, first instance that we can take is, say, your value of zeta. We are trying to make a table. The value of zeta is one thing. Then based on that, the pole location can be another thing. Pole location. Okay, so then your step response. Step response. Okay, so first value we can take is, we can take zeta equal to 0. Okay, so if zeta equal to 0, what we left? If zeta equal to 0, this portion will be vanished, so there will be no exponential decay. And if zeta equal to 0, it will minus 1 root over minus 1 will be actually, then we will have plus minus j omega. So if zeta equal to 0, we have plus minus j omega n. So what does it mean? A pure oscillation. So from this one, we are going to get a pure oscillation. Without decaying, we will have a pure oscillation. Okay, so this is case 1. Now, next case is if your value of zeta is in between 0 and 1. Okay, so if it is in between 0 and 1, this portion will be always negative. So root over negative will be giving you always some imaginary portion, as well as this one will be also there. So what we have here is we have real portion as well as we have imaginary portion. So basically complex pole location we are going to get. So say here we have our two uh, complex conjugate poles. So this location here is minus zeta omega n, and this is your since this value is negative, you can just invert. So we can say that it can be omega n root over 1 minus zeta square. Okay, and then we put a j here. So you'll have plus j omega n root over 1 minus zeta square and minus j omega n root over 1 minus zeta square. So what kind of response we're expecting? We're expecting a damped oscillation. So that is why this is called, so the previous one is undamped. Now we are going to have a, going through a damping to the final value. So under damped scenario, under damped. Okay. Now case 3, if the zeta value is 1. So if zeta value is 1, so this portion will be 0. So you have two poles in the same location. Okay. So actually the first one also you can show in terms of location like this. So now what we have, the two poles in the same location in the real place. So what is the name of that one? In the same equal. So this is called critically damped, isn't it? So critically damped. So we'll have a response something like this, very fast going to the final value. So minus zeta omega. Or basically omega n, because the zeta value is 1, isn't it? Okay, sorry, this is zeta value. Okay, third condition is if the zeta value is greater than 1, then what will happen? So if the zeta value is greater than 1, that means this portion is positive. So we'll have minus zeta omega n plus omega n root over zeta square minus 1, or minus zeta omega minus omega n root over zeta square minus whatever the value of the zeta above 1. So actually we'll have overdamped scenario, one scenario here, one scenario there. So we can call this one as this value, and this one as this value. Okay. So based on that, what we are going to get a delayed response going towards the final value. Okay, so this is overdamped. So this was critically damped, and this is overdamped. Okay, so this is how pole location is actually related to your zeta. Okay, and based on these values of zeta, we can actually easily predict the system behavior. So if the value of zeta is 0, system is oscillatory or undamped. If the value ranges in between 0 and 1, then it is underdamped, an oscillation going to the final value, damped oscillation going to the final value, and then you have other two cases, zeta equal to 1, critically damped, and zeta equal to greater than 1, and overdamped. Okay, so let us look at one example, example 4.3. Sorry about this, example 4.3. What was given here is a transfer function given, GFS equal to 36 by s squared plus 4.2s plus 36. So now we have to identify and figure out the value of zeta and omega n. So definitely very simple. Omega n square is 36. So omega n is 6. What about zeta? Zeta, this parameter here is actually twice zeta omega n, isn't it? So twice zeta omega n equal to 4.2. So zeta will be 4.2 divided by twice omega n. So 4.2 divided by 2 into 6, that will be approximately 0.36. Now 0.36. So what should be the system type then? What kind of response we are expecting from this system? So from the zeta value, we can actually predict that, isn't it? So zeta value is 0.36, which is in between 0 and 1. So basically a damped oscillation we are expecting. Now what does it mean? You will have a under damped response. Okay, so let us look at next example, example 4.4. Basically, example 4.4, three different transfer function is given to us. So one is 12 divided by s square plus 8 s plus 12. This is one. Then next one is 16 divided by s square plus 8s plus 16. So one thing you have to carefully observe whenever you're solving something, it's better always to observe. So observing makes things easier. So what we're changing? We're changing only the natural frequency here. The problem is changing only the natural frequency, that is omega n. So zeta value is accordingly will be changing. Okay, so let's look how it works. So you have 20 divided by s square plus 8s plus 20. Okay, so to figure out, you can actually previously, whatever the transfer function we had, that is s square plus as plus b equal to 0, that characteristic equation. So we can actually take help of this one as well if you want. Okay, so what we know is a equal to twice zeta omega n. So if you want to figure out zeta, so it will be basically simply a by twice omega n. And what is omega n? Omega is nothing but root over b. So you can also directly using this formula, you can actually check the system's behavior. Okay. So let us look at the first one. So zeta equal to a is nothing but 8. So 8 divided by root over 2. 2 is from the formula and b is 12. So this is case 1. So case 2, zeta equal to 8 by 2 root over 16. Third case is zeta equal to 8 by 2 root over 20. So as you can see, we in the problem, only thing that has been changed is the omega n, but because the a value was kept constant, but even though omega n was changed, it inherently changes the value of the zeta. And accordingly, the system behavior will also be different. Okay, so what are the values now? If you calculate this one, you are going to get 1.1547, something like this. If you calculate the second one, then you are going to get the values for 8 by 8, that is 1. And the third one will give you 0.894. Now, what type of system behavior actually we are expecting from this one, system's response? So definitely this is greater than 1. Zeta value is greater than 1. So greater than 1 will give you over damped scenario, over damped response. So this is equal to 1. So all, both the root will be same. So basically this will be critically damped response. One thing about the critically damped, it will be always a suitable, nice looking function, so that you can always have something like this. Okay, so repeated roots. Third one, the value in between 0 and 1. So basically now this will have under damped response. Under damped response. Okay, so from the pole location, the pole location is also a function of the zeta and omega m. So pole location can be related with the system parameter here. We have two system parameter for our second order system, that is zeta and omega n. Zeta is the damping ratio, and the omega n is your natural frequency of oscillation. So based on this one, we have four responses, and the four response will be determined based on these parameters. Okay, so then you have also one skill assessment exercise, skill assessment exercise 4.4, similar thing. The value of zeta omega n you have to calculate, and based on that you have to determine what is the system response is going to look like. So so far whatever we have seen, the skill assessment exercise of this chapter is relatively easier. So I think you can go you can cover those by your own. So this is the end of the article 4.5. So we can, this is finished. So we can start the next one, but next one may take a more longer time. So I think 1 hour is already elapsed. So I think we should go for the next topic in the next class. So the next topic is 4.6, that is under damped system, second order system. So basically all the equations related to the under damped case will be discussed, derived and discussed, and how they are related to the other system response as well. So as I already said, this chapter is very, very important for clearing your intuitive ideas. So if somehow you fail to do that, so it will be very, very difficult to continue with the course. So I'll ask you, that is why also deliberately I'm keeping the topics small in this particular week, even though 1 hour, but I'm not covering too much topic. I can, if I want, I can cover a few more topics, but I'm keeping it short as possible. Okay, so see you in the next class, inshallah.